So, in this class we will study about the X-ray diffraction from crystal X-ray diffraction from crystal. This is very important in the sense that this is the only method which is used to determine the crystal structure experimentally. Okay. So, if we have a material, unknown material, and if we want to know the structure of that material, so one has to use this X-ray diffraction from that crystal to then you can find out the structure of that material. Okay. So, in that sense it is a very important. So, it is a experimental aspect. So, here X-ray, so you must be familiar with the X-ray. What is X-ray? X-ray is a electromagnetic wave, just like visible light. So, visible light have, see it is the similar to visible light. Only difference is the wavelength or frequency. So, visible light, you know, this wavelength is in the range of 400 to 700 nanometers, right. And X-ray, this wavelength is, I think, is in the range of 0.1 to say 1 nanometer. So, in this range close to this. Okay. So, 0.1 nanometer is basically 1 angstrom to 10 angstrom. In angstrom unit one can write 1 angstrom or 10 angstrom to 10 angstrom, and this 4000 angstrom to 7000 angstrom. So, it is very small wavelength compared to this visible light. And how X-ray is generated, that hopefully you know, but still I will mention, because for this experiment we use X-ray source, and which type of source are used, what are the wavelength is selected. So, that let me tell you. So, this in X-ray machine, basically we have a X-ray tube. It's X-ray tube means it's a vacuum. It is a vacuum tube, means air is taken out from that tube, right. It is under vacuum, and now at one end of the tube, inside tube, at one end is the cathode is there. So, basically this type of, so this is the filament. So, current will flow through the filament, and one material is here. So, it's we tell cathode. So, basically this filament, this hits this cathode material, okay, which emits electron, So, from this cathode, so electron will be emitted, and now we have anode, means we have target. So, that the target is generally we use this molybdenum target, copper target, molybdenum, copper target is used for this X-ray generator. So, now this electron is emitted, but we want this electron should be accelerated and hit this target. When it will hit this target, then from this target anode, from this anode X-ray will come out. So, X-ray will be generated there and it will come out. Okay. So, how it is generated I will tell you. So, that means to accelerate the electron, so we have to apply voltage difference between these two, right. So, this anode is connected with this positive terminal of battery and this other one is negative terminal. So, electron will accelerate it and hit the. So, this whole system is kept in a tube, whole system is kept in a tube and this tube is under vacuum, okay. Because if it is not under vacuum, so if air is there, so it will collide with air molecule, so it will be scattered in different direction. So, that we do not want, so it should accelerate and directly hit this our target anode material, okay. So, when it will be accelerated and hit this material. So, what will happen? So, two things will happen. So, these electrons will penetrate the material and it will be deaccelerated, it will lose energy, right. So, when any charged particle is accelerated or deaccelerated, it emits electromagnetic wave, right. So, that is the principle, it emits electromagnetic wave. So, when this charged particle penetrating the target anode, okay, so it will be deaccelerated, it will lose energy and that energy will come out as a electromagnetic radiation, okay. So, that is we are telling is X-ray. So, because its wavelength generally become very small, it cannot be in the range of visible light. So, this X-ray is coming out, this electromagnetic radiation is coming out, okay. So, if I draw intensity of X-ray, whatever coming out, the intensity of this X-ray versus this wavelength versus this wavelength of this X-ray. So, it is this type of curve one can see, okay. So, its intensity is maximum at a particular wavelength, but simultaneously it has a minimum wavelength, and another things happens when this accelerated charged particle hits this target. Now, this target are made of atoms. So, now this is either is made of molybdenum or copper, some other target can be also cobalt, people use also cobalt, okay. So, conventionally these are the target we use in our laboratory X-ray generator. So, this target having the atoms, and atomic structure you know, right, atomic structure you know, it has K shell, L shell, M shell, right. So these electrons also hits this electrons of this core shell, and it take out from that cell. Then again from higher cell electron jumps to the lower cell. So then that energy difference comes out as a electromagnetic wave, and that wavelength is generally in the range of, for this material, in the range of X-ray. Okay. So its nomenclature is like this is K alpha. If electron jumps from L to K, so it is K alpha X-ray. If it is jumps from M to K, so it is called K beta, right. If it jumps from M to L, so it is called L alpha, right, etc. So you will get the K alpha, K X-ray, L X-ray. So these are called these characteristics X-ray. These are called characteristics X-ray. Okay. So because it depends on the atom. Okay. So its energy difference are fixed. So its wavelength also fixed. So apart from this X-ray, this is called continuous X-ray. These are called continuous X-ray. This is because of deacceleration of the accelerated electron in the material when it is penetrating through the material, and from there you will get this continuous X-ray, and also you will get this the X-ray characteristics X-ray. So it will come, as I told, this only different. It will come only different. So this energy difference, yeah. So it will come from different energy levels. So its wavelength is fixed. So here you will get, say here you are getting this type of peak. Generally, this type of peaks you will get. Then you are getting this type of peaks, okay, etc. Okay. So overall, whatever the intensity we will see, that is the summation of these two intensity, and basically you will see at this position. Let us see. Okay. At this position, at this wavelength, you will see this. Okay. So whatever the X-ray spectra you will see, overall X-ray spectra you will see, that you will see this type of variation of the X-ray intensity as a function of wavelength, So these are the characteristics X-ray, K beta, this is K alpha. So why it is K beta, K alpha? Because for K beta this energy difference is higher, so wavelength will be smaller. So it is coming at lower in wavelength side, and K alpha is coming at higher energy side. Okay. So this you can see these characteristics X-ray are having the highest intensity, and K alpha is generally have the highest intensity. So if one want to choose a particular wavelength of X-ray from this X-ray spectra, so generally we should prefer to choose this K alpha. So if target is copper, so we tell copper K alpha, copper K beta, right. So copper K alpha, again K alpha have two component, K alpha 1 and K alpha 2. So that is because of this S cell, this the again this shell are subdivided, right, into subcells. Okay. So, because of that, so this some minor change of energy it is there, k alpha 1, k alpha 2, but for the timing you forget, just take as a k alpha. So, copper k alpha, this wavelength of this copper k alpha is 1.54 angstrom. Okay. But if you take this molybdenum source, so this copper k alpha, this is for molybdenum source, and if you take cobalt source means target here, cobalt target. Okay. So, then this yeah, so 0.7, yeah, around 0.771, 0.71, we write 709, accurately it is 7.709 angstrom. Okay. It is the angstrom. Okay. That is the molybdenum k alpha, wavelength of molybdenum k alpha. Okay. So, this just in our laboratory, whatever the X-ray we use, whatever the target we use, and from that target when we choose a particular wavelength, so we choose copper k alpha. So, that wavelength is fixed, nobody can change, it does not depend on anything. Okay. If it is, so it is the characteristic X-ray and it is fixed for that particular target. Okay. So, this way X-ray are generated. So, and here this voltage range, it is in kilovolt range, that the relation, probably this lambda equal to 12.4 by V. So, when V will be in kilovolt, then angstrom, this lambda will be in angstrom. Okay. So, if we use 12.4 kilovolt voltage, 12.4 kilovolt voltage, okay, then you will get wavelength, that minimum wavelength you will get, that is 1 angstrom. Okay. So, so to get the minimum wavelength, so one can estimate this how what is the voltage one required, but this intensity, since this wavelength does not depend on this voltage characteristics X-ray wavelength, it does not depends on the voltage, but what depends on the voltage? Depends its intensity. If I want to choose k alpha and with higher intensity, so we have to if we apply the higher voltage, so then what will happen? So, accelerated energy will be higher, so more electron will go and hit the target, okay, and you will get more and more X-ray, so intensity will be higher. Okay. So, here just I wanted to say that in X-ray machine, generally that voltage we apply between the cathode and anode, so this voltage in the range of kilovolt. Okay. And the target we use, that is generally this type of target we use. The for X-ray diffraction, generally we choose wavelength that is generally this copper k alpha or molybdenum k alpha or cobalt k alpha. Okay. So, these are the practical aspect I told you, apart from the principle of X-ray spectra. So, so this is about the X-ray. This is about the X-ray. Now, here another question is there. Let's sometimes for experiment we use we need all sorts of wavelength of X-ray. So, then there is no problem. So, from the target whatever the X-ray is coming, so that will have the all sorts of wavelength, So, this we tell it is a white X-ray, because it has all white light, it has all wavelength, white X-ray it has all wavelength. Okay. So, sometimes for experiment we need white X-ray having all sorts of wavelength, and another X-ray we also use that is of one wavelength. So, that is called monochromatic X-ray, monochromatic X-ray, monochromatic X-ray. Okay. So, monochromatic X-ray. So, for monochromatic X-ray, then since X-ray source always giving this type of spectra, we have to choose one particular wavelength. So, there are different ways to choose that one. So, we use sometimes there is called filter absorb. So, it basically absorbs all wavelengths except one wavelength. So, it gives then it's that that basically it just pass one wavelength absorbing all other wavelengths. So, that type of filter are available, and for different wavelength different filter are used. This is one way. Other way is I will tell you later on, because generally if we take mirrored reflection. So, this is called Bragg reflection, that I will tell you later on. Now I cannot say, because before that I have to tell you something more. So, for X-ray diffraction from the crystal, we may need white X-ray, we may need monochromatic X-ray. Okay. So, then diffraction. So, you are also familiar with the diffraction, you are also familiar with the diffraction. Right, light electromagnetic wave, okay, electromagnetic wave, light, it is wave. So, it shows the interference, diffraction, right. So, interference diffraction, that basically what is interference? These two waves are coming, they overlap, and then interestingly they show the that resultant intensity are not the uniform, it is not the just summation of these two. Okay. So, it shows the nicely variation of intensity, right, variation. So, we tell bright, dark, bright, dark, bright, dark. Okay. So, when these two waves, electromagnetic waves, light, visible light overlaps, okay, they interfere with each other under some condition. It does not happen always. So, there are some condition, you know, this it has to be coherent. These two coherent waves, if they overlap, then only you will see the interference. Okay. What is the coherent? Coherent waves, basically this between these two waves, all the time the phase difference between these two waves that will remain constant with time. So, it will not change with time. Okay. So, wave are moving, whatever the initial phase difference between these two. So, all the time this phase difference will remain same. So, then we tell that they are coherent source. Okay. So, they will interfere, they will overlap, means they will interfere, and you will see the nice distribution of light, intensity distribution of the light. So, you will see bright, dark, bright, dark. So, these are called basically fringe, right. So, these are called basically fringe, interference fringe. Okay. So, So, this where this bright fringe we see, where this dark fringe we see. So, when if at this it depends on position, you know. So, because this light are coming, they interfere. So, they are from the source they are coming, right. So, when so depending on the position, okay. So, there will be path difference between these two waves, there will be path difference between these. So, here whatever path difference, here this path difference are different, here path difference are different. So, when this path difference is multiple of lambda or phase difference is multiple of 2 pi, then we tell this constructive interference, there will be constructive interference, and we will get the bright peak, okay, bright fringe. And when path difference is multiple of lambda by 2, okay, multiple of not multiple, odd multiple of lambda by 2 one can say, or the odd multiple of phase difference is odd multiple of pi, then you will see this. So, they are out of phase, we tell out of phase, so they will destruct each other. So, you will see destructive interference. So, this is the interference. And diffraction is basically the interference among the secondary waves, you know. What is secondary waves? So, basically waves are coming we tell plane waves are coming, means on this plane this phase are same, on this plane this whatever, if we draw plane here, so phase are same. So, then we tell it is plane wave. So, plane wave is coming and falling on some obstacle, you know, falling on some obstacle. So, this obstacle have some hole, this obstacle have some hole, this obstacle have some hole, okay. So, when there is a hole on this obstacle, so it pass through it, okay, it pass through it, yeah. It pass through it. So, when these holes are comparable with the wavelength of light, okay. So, it is just not, it does not pass like just as it is. So, here it feels some obstacle. So, we tell generally people tell this, it bends, okay. So, it bends from its from this direction, it bends to other direction, okay. So, so that generally we tell diffraction, but it is not the good way to define the diffraction. So, what we tell that whenever wave comes here, this obstacle, it face some obstacle, although hole is there, but wavelength is comparable to this hole. So, here we tell this is the source, it acts as a source and it generates waves, okay. Similarly, from each hole, so these we tell the secondary wavelets. So, it is the primary wave is coming and then getting obstacles. So, then this each point this act as a source and they emits the waves. So, these waves are called the secondary waves, okay. So, So now they overlap, these secondary waves, they are coming from different holes. So they overlap. Okay. So this, because of this whatever the overlap, so that we are telling that they interfere with each other. So this basically interference among these secondary wavelets is basically here whatever we will see, that is the diffraction. So if it is here, basically I have drawn this the grating, right. So it has grating, so it has many holes. Okay. So if you had, if this obstacle have only one hole, so it is a single slit diffraction. If it has two holes, then we tell double slit diffraction. If it has many holes, then we tell it is a grating and grating diffraction. Okay. So, and that distance between these two, so middle to middle, if we define by D, so this we tell is grating element D. Okay. Now, here we will get the basically interference among these secondary waves, and here in case of gratings we will get interference pattern, you know, this as we have seen for as I drawn earlier. So, but this intensity distribution will not be like this. So, it is modulated with the diffraction pattern of the single slit interference diffraction. So, it is basically let me okay. So, here it is basically you will get intensity distribution is like this. So, all will not have the equal intensity as we have seen earlier for interference case. So, here interference peak I am getting, but their intensity is varying, their intensity are varying. Their intensity are varying. Okay. So, these peaks are basically we tell principal maxima. We tell principal maxima. So, it is equivalent the interference bright peaks. Okay. They are equi-spaced, and why do we get this? The picture we have I have drawn that this is the intensity versus this angle theta. Okay. What is the angle theta? So, it is basically with the incident one. So, whatever this okay. So, it is forming a different angle, different position. Okay. So, we tell diffraction angle, diffracted angle. So, this it satisfy this condition d sin theta equal to m lambda. Okay. So, d is the getting element, theta is this basically this diffraction angle theta. So, at different angle, at which angle we will get the maxima. Okay. So, if for a particular wavelength whatever when it will satisfy this condition, so we will get different maxima starting this value for m 1, 2, 3, 4. Okay. So, we will get many maxima depending on the first order, second order, this is the order, m is order of the interference or diffraction. So, this m equal to 1 first order, second order, third order peaks. So, from getting and diffraction, in getting diffraction of the wave visible light, we get this type of change of the distribution of the intensity. Okay. And that follows this expression. Okay. So, these are the very important relation where basically here this relation is basically one can get the information of the about the gating element, also one can get information about the wavelength if theta is measured and one of them is known. So, other one can be find out from this gating experiment. So, I think I will stop here, I will continue in next class. So, thank you very much.